Okay, so now we're getting into chapter 8.3, which is all about annihilators. Really cool name for a chapter, I think. But this is the section that everybody hates. The reason being, it's confusing. There's a lot of terminology. There's too many tables. There can be just one table, and that would be fine. But there's just a lot of stuff going on in this chapter. A lot of generalizations that they make at once, and it's really tough to read through the book and actually understand what's going on. And so I want to give just a brief introduction to why we care about these annihilators and what they do, but I don't want to spend too much time going into the details. I actually want to go through and just do example problems of cases that turn out okay, which is why I've titled this one "Everything is Fine." We'll do another video on when things aren't so nice, but this is just, a general case here. And so we saw with 8.1 and 8.2, we were working with homogeneous differential equations, right? So we know how to solve those pretty easily with, using the exponents that we know of to solve all of these equations. But now we're going to focus on the case where we don't have 0, but we actually have some function f. This will give us, once we figure out how to solve these, it'll give us a wide range of applications we can use it towards, like spring and mass you've already seen in lecture. And so it's pretty helpful, I think, of a topic to learn how to do. But it involves a lot of guessing, which is why some people don't like this chapter very much. But so just some motivation here. We have some linear differential operator. I'm going to call it L of D, same thing as just L. Operating on y, and in this case we don't get 0, we get some outside function, okay? But we don't like this. We already determined that it's a lot easier if this f was equal to 0. So we ask ourselves, can we make, and I'll put make in little quotation marks here, can we make f equal to 0? Is that something we can possibly do? And this chapter says yes, you can. You can use what's called an annihilator. So what if I go ahead and just apply something to both sides? This thing a of d. So it's a differential operator just like L. And then we define a of d to mean the very operator that we use on f to get 0. So what I'm able to do here is if I can find this a of d, what I can do instead is I can just solve this one here. So I pretty much, that's a colored pencil. 1 second. I pretty much just tack on this operator here, this a of d operator, onto the one they gave me. And then I see it will give me 0. So I can solve it in the way we've been solving all of these things before. And so what we can say then is that if we were to just take this apart, if we solve L of D, it would give you the complementary function. So we saw that that was the functions here that solves Ly gives me 0, okay? And then we also can say that this A of D term will give you your particular solution, okay? And that's the one Ly is equal to f. Okay, so this is just, where this stuff that we're about to do is coming from. I wanted to give at least a little bit of motivation behind this. What we're able to do now is you can see this table that I've screenshotted from the chapter. They're allowing us to just bypass this whole process here of, multiplying both sides by this new operator that annihilates f, and just pretty much go right to the step and output our particular solution. So somebody's done this a whole bunch of times and found a pattern. This pattern's illustrated here in this table, which we'll be using in a little bit. So you don't really have to be working with annihilators all that much. You just have to know how to identify your particular solutions based on this f that they give you. Okay. So what we're going to do first is we're going to outline the process by which you solve these equations. Okay. So the exam questions and homework problems will read, I don't want to do that. They'll read something like, find the general solution to Ly is equal to f, okay? So they give you some non-homogeneous differential equation. The general solution they mean here to be the complementary function plus your particular solution, okay? So that's your general solution here. So what we first need to do is we need to find y of c, okay? And this is the easy thing. This is what we do. We solve the homogeneous differential equation, Ly is equal to 0. So we ignore f for a little bit, and we just use the techniques from the last video and from sections 8.1 and 8.2 to figure out what y sub c is, okay? So that's our first part here. That's going to be simple. What we do next is we guess a particular solution based on this table here. Okay, this particular solution is y sub p, okay? And so what you'll see, and we'll talk about this table a bit more, and I can't write on it without messing it up, but they have this f of x column here on the left-hand side, okay? That f of x here corresponds to the outside function that they give you, okay? So what you're going to do in step 2 is you're going to go through and find in this table on the very left-hand side the case that corresponds to what they gave you for your function, and then you're going to try your usual trial solution, okay? So this video will focus on your usual trial solution and what happens when that actually works out for you. Next video, when stuff gets messier, we'll work with the modified trial solutions, okay? But for now, we'll be using just the first and second columns of this table. That will give you your particular solution, okay? But we're not quite done. So once we find that particular solution, I need to solve for the coefficients of my particular solution. So I'm going to find a particular solution here. And if you look at the second column, you'll see that there's these a naughts, a sub k's and stuff. Those are the coefficients that I need to solve for. And I need to solve for them so they actually match up and give me this f when I send through my entire function, okay? So that was kind of a lot and it was kind of quick, but hopefully with some examples, we can figure out exactly what to do here. Okay, so the very first one, let's go ahead and make it pretty simple. Let's do y double prime plus y prime minus 2y is equal to, not 0 this time, but 5e to the 3x, okay? So my first step here, I need to find the complementary solution, which is solve the homogeneous equation. So I ignore my f that they gave me, and I write y double prime plus y prime minus 2y gives me 0. So I factor this out to be d squared plus d minus 2 applied to y gives me 0. This corresponds to r squared plus r minus 2 gives me 0, or in other words, my roots are, or it factors down to r plus 2, r minus 1. So I have my root 1 here. r1 is equal to negative 2, and r2 is equal to positive 1. And we know from last video, these are distinct real roots, so I stick them in, and my complementary function becomes exponents raised to those powers of the roots, okay? If this looks foreign to you, then go back and watch the last video first. That will help a lot. But here is our complementary function, okay? So we've done this part. Now what we're going to do is we're going to guess a particular solution based on the table they gave us, okay? So let's look at what our f is. We were given y double prime plus y prime minus 2y is 5e to the 3x. So my f is going to be 5e to the 3x. All right, so I go up to the table, and it looks like the top case, the very first case here. What they've done, if you read the text between the two tables, they've simplified the top table down into usual cases. So we'll be using the bottom table quite a bit more in this course because it's simpler. But it looks like the top case there. So we have a constant and then e to the ax. So we have this condition here that as long as this is already not a solution to my complementary function, so as long as 3 here was not one of my roots, then I'm good to go. And it tells me to use my particular solution, y sub p, is equal to some constant that I need to solve for, e to the 3x. And you might say, you know, what happens if it is a root? Next video, okay? All right, so there's our particular solution based on the table. We've done that part now. And lastly, we have to solve for the coefficients. Now, how do we do that? Well, to solve for the coefficients, I have to send through y of p through my differential equation. So to solve for a naught, I plug in y sub p to my differential equation, which was y double prime plus y prime minus 2y is equal to 0. Okay, so I do that, and then I'm able to solve for a naught. And I made a mistake here. This should not be 0. This should be 5e to the 3x. So I plug it into the non-homogeneous equation, and then I'm able to match these coefficients here. So this a naught and this 5 will, you know, allow me to solve for a naught. So I take two derivatives. I take 9a naught e to the 3x. One derivative is plus 3a naught e to the 3x, and then minus 2 times e to the 3x gives me 5e to the 3x. And so, you know, they all have the exponent, so I can just look at the coefficients. This should not be a 2, it should be a 2a naught. Minus 2a naught. And then you'll see here, if I combine these, I get 10a naught is equal to 5. Okay, so the exponents go away, which tells me that a naught is equal to a half. The reason I need to go through and solve for a naught is because I need to make sure that it matches up with the outside function that they gave us here. Okay, just one more time. So I have my general, or I don't have my general solution. I have my complementary function here. I have my particular solution here, and I've solved for its coefficient, so I'm ready to give you the general equation. So my general equation y of x is again equal to the complementary function plus my particular solution. So it's equal to c1e to the minus 2x plus c2e to the positive x, and then plus 1/2 e to the 3x. And I'm done with the problem. This is my answer here. So that was pretty much it. You know, a lot of the hard work came from identifying the table, from the table which particular solution we should use, and also solving for the coefficients. So we're going to do a really messy one now that involves solving for the coefficients, because that often is the hardest part of this problem. So our next example, let's do y double prime plus 2y prime plus 5y is equal to 3 sine of 2x. Okay, so you might look at this polynomial on the left-hand side and already know that we're going to have imaginary coefficients, but we'll go ahead and go through the steps anyway. Not imaginary coefficient, sorry, imaginary roots. So I need to find my complementary function, which means solve the homogeneous equation. So I have y double prime plus 2y prime plus 5y gives me 0. I'm going to skip right here and say, no, I'm not, because I need to do this. D squared plus 2d plus 5 applied to y gives me 0. And so my auxiliary polynomial is r squared plus 2r plus 5 gives me 0. So quadratic formula, negative 2 plus or minus the square root of 4 minus 20 over 2a. gives me -1 plus or minus 2i. So I've got two distinct roots here. R1 is -1 plus 2i, and R2 is equal to -1 minus 2i. And I know that I can just look at a table or from my memory and know exactly what solutions these correspond to. So my complementary function here is just c1 e to the -x sine of 2x. Well, I think cosine comes first, but either way. Cosine of 2x plus c2 e to the -x sine of 2x. Okay. If you don't know where those came from, go back and watch the other video first. And that's my complementary solution, or complementary function. Okay. So now I need to find my particular solution. So I go up and I figure out what f was. F is this thing here, which is 3 sine of 2x. So here I go to the table, and I see which of these on the left-hand side look a lot like the f that they give me. So it looks like the middle row on this bottom table here, the c sine of bx. It's asking me this condition here. It says that if my polynomial differential operator of IB is not equal to 0, then I'm good to use the solution they offer below. So let's go ahead and check that just so we can get in the habit of doing that. I need to make sure that P of IB, B in this case is 2, and I plug that in here. Okay, so this was my P of D, if you remember. And so I get 2i squared plus 2 times 2i plus 5. So here I get -4 plus 4i plus 5 gives me 1 plus 4i. And that's obviously not 0. Okay, so I checked their condition that they gave. And so I'm allowed to use the particular solution. That's that linear combination of sines and cosines. All right, so that tells me that y of p should equal a naught cosine of 2x plus b naught sine of 2x. Okay. So what do I have to do with this? If you remember, I have to solve for a naught and b naught. And how do I do that? I have to plug that in to my differential equation. So I have to plug yp into y double prime. Where did it go? Plus 2y prime plus 5y is equal to not 0, but my function they gave me. It's like this. And that will allow me to solve for a naught and b naught. So this will be tedious, right? Because you have to take two derivatives. So I find it helpful to just do all the derivatives before you try to add anything together. So let's start with the particular solution again. A naught cosine of 2x plus b naught sine of 2x. Okay. If I take the derivative of that, cosine goes to negative sine, and sine goes to positive cosine. Okay, so there's y prime. And then yp double prime, I take just one more derivative, so I get -4 a naught cosine again, back to cosine, and then -4 b naught back to sine. Okay, and then what I do, and I like to do this vertically just for space, but now we have to, go through and actually figure out what this quantity is. So what I like to do is I like to just put y double prime on this side, which was equal to -4 a naught cosine of 2x minus 4 b naught of sine 2x. And then again over here, I'm adding to that 2y prime. And so y prime was negative 2a naught, that stuff right here. So 2 of that is plus 4 b naught cosine of 2x minus 4 a naught sine of 2x. So same thing, I just did them out of order because I want my cosines and my sines to be the same vertically so I can add them easier. All right, and then I need to add to that 5 times just the particular solution itself. So this becomes plus 5a naught cosine of 2x, and then plus 5b naught sine of 2x. Okay, so this entire sum, these 6 terms will add up, and we can go ahead and say what that equals. I can factor out the cosines, so I'll get 4b naught plus a naught times cosine of 2x. And then I get for sine b naught minus 4a naught sine of 2x. Okay, so we did all of that. That was just the left-hand side of my equation here. So I still have to equate it to my 3 sine of 2x here. All right. So I have to write that as equal to 3 sine of 2x. And then what's helpful to do here is to just write 0 cosine of 2x. Okay, because that's actually what this is. You can add 0 times anything, so this at least helps me visualize what I need to do. So you'll notice now that I have to group my like terms, which means I have to match my coefficients across the equal sign. So I know I have 0 cosines on the right-hand side, which means that 4b plus a naught better give me 0. And then I know I have 3 over here in front of the sign, so I know that b naught minus 4a naught better give me 3. So I can go ahead and write those equations out. I have 4b naught plus a naught gives me 0, and then I have b naught minus 4a naught is equal to 3. So I'm going to go ahead and just solve for b naught on this side. B naught is 3 plus 4a naught, and then I'm going to plug it in on this side, and I'm just going to go back to black ink here. So I have 4, b naught is now 3 plus 4a naught plus a naught gives me 0, and that tells me that a naught is equal to negative 12 over 5. Let's see. No. Negative 12 over 17. Yeah, okay. Yeah, okay, sorry, I'm losing my mind a bit. Okay, great. And then b naught, I can go ahead and just plug in either of these equations here or here for what I want it to be, and I'll find it's equal to 3 over 17. Okay, so I know that this combination of a naught and b naught gives me exactly what I need on the right-hand side. So I say that my particular solution is negative 12 over 17 cosine of 2x plus 3 over 17 sine of 2x. Okay, and finally, coming to a close here, we combine that with our complementary function here. So then my general equation here, y of x, is my complementary function, which is c1 e to the minus x cosine of 2x plus c2 e to the minus x sine of 2x was my complementary function. And then my particular solution, to make sure I get the f on the right-hand side, is this equation here. So plus 3 over 17 sine of 2x. So I wanted to show you with this equation here that some of the difficult parts of these problems are not actually the differential equations. They're just solving for these coefficients, right? I myself, when I did this problem before presenting it here, I made a mistake solving for a naught and b naught, and it took me a few minutes to figure it out. And so this is just like the general case, though. You go through, and as long as you do these three steps here, you'll be golden. The one thing that we'll explore next video is what happens if the condition in the middle column fails and you have to use the modified trial solution. So we saw down here, for instance, that the condition was that this could not be equal to 0. Well, if it was, then you have to do something else, and we'll talk about that next time.